Our next speaker is Sreenivas Gollapudi from Google, and he's going to tell us about computational mobility, learning, prediction, and algorithms.
Thank you all. Good morning, and my name is Sreenivas Gollapudi. I work at Google, leading a small team that focuses on problems related to geographical information systems. Being a computer scientist, call it computational mobility. And why? Because there are a lot of areas, as we'll talk today, that fall under this rich area, which is open to a lot of research and future directions. So what is it that we are interested in? So to begin with, I'm not going to talk about any specific problem. I'll give you an overview of all the work that we do here, hopefully get you interested in working on similar problems. So what we're looking at Google is basically looking at this entire problem space and from the filter of a universal transportation system, right? So what do we mean by that, right? By that, what we are beginning to understand is as people move around in the network, people are looking for objectives beyond simple time and distance, right? There are a lot of adaptive, customizations that people are really looking for: safe routes, simple routes, familiar routes, etc. But to add to this, complicating this is basically the inherent dynamic nature of this network. Okay, so there are a lot of closures, there's traffic, the network itself changes with new constructions, new points of interest showing up in the network that people could be interested in visiting, etc. Right? So basically, you can break this up into three categories. One is, first of all, what is the network that we're dealing with? So that's learning the network state. You can probe, you can get a lot of signals from the network, speed sensors that the cities provide, etc. And a combination of these. We'll talk a little bit more and as we go forward. And then, of course, the state itself, since it's dynamic and it's large, because the network itself is large, how do we represent the state in a succinct way that we could potentially use at runtime? Okay. So what we call learning representations of this network embeddings and such from the machine learning world. And then, of course, finally, what do you do with the state? You act on the state by providing some solutions, finding quickly the number of alternate ways to reach a particular destination, for example, doing multi-objective routing, safe but fast, safe but scenic, and so on and so forth. And of course, new routing paradigms are coming now, like the EV routing is becoming very, very important as the EV adoption actually, takes off now. So, and basically, and then we have this new, what we call network optimizations, like what we call social routing, maximizing social welfare and such, where we take user preferences, but we don't really, think of fairness is one example, right? But what are models of these preferences that can be included in what we call global objectives, right? In the end, we want the whole network to be stable, performant, throughput is high, and latencies are small, okay? Now, again, given the scale, obviously, we have the system side of things of doing all this with low latency and memory, okay? So clearly, as you can see, many of the ideas that come towards looking at these problems and modeling these questions, they arise from a lot of areas we are familiar with to a certain extent. Like the classical graph algorithms, we have game theory in terms of incentives and fairness and cost, congestion routing, and so on and so forth. Of course, machine learning to learn, dealing with uncertainty, classical optimization, and then distributed algorithms to run these systems efficiently. Okay. So I'll give you a flavor on the transportation platform side of things. One of the things that we all know is the scale of these graphs. I mean, this, millions of nodes, billions of edges and such. So we need to be able to deal with this at runtime on machines that we serve any path search query on, for example, right? And for that, we need to be able to do a lot of pre-processing that we're allowed. And so that at runtime, the queries become fast, the state becomes manageable, okay? So one of the things that, one of the team members worked on is partitioning these networks. And then we actually had to use some clever combinations of walks, random walks, and max flows to produce some very nice balance separators for these networks, okay? And this is actually being used in the production system today that has significantly improved the performance of the system, okay? And of course, details of this are available in a blog post. And the architect of the solution is sitting here in the audience, so Ali Sanop, so you can talk to him later during the course of the day. Similarly, another important functionality that these systems should be able to support are, like what I said, customizations and some degree of robustness. By that we mean deal with changes, right? When things fail, I still need to be able to route. You can't just say there's no route available, for example, right? A lot of customizations, user preferences and so on. And again, here Ali was able to produce some excellent work on using electrical for decompositions, using fast Laplacian solvers that has recently come up in the theoretical literature. And we are actually able to now produce a lot of alternate paths between any 2 points extremely efficiently on these large systems, right? These large graphs, these large networks. So that's another very interesting application of theory. And in fact, we had to even make some advancements there to actually have this work in our systems. And then something most of you are also familiar with are these distance oracles. Can I get a notion of an approximate distance? I mean, we don't need to get the exact shortest path, but if I can get some approximate distance very quickly, what can I do with it? And we are sure that this is going to enable a lot of applications for us. And then there are some directions we're exploring in this space as well. So again, what is a classic example of customizable routing? Let's look at EV routing that's coming up. And now these are solutions that are coming up in autos that are embedded in these vehicles, right? So there are vehicles that actually route you through stations automatically based on the distance you're traveling, time of day, the state of the vehicle, and so on and so forth, which makes the problem very complicated, okay? I mean, Kuller and his team worked on this problem, a similar problem called the gas station problem in earlier part of this decade, and or last decade rather. And this is an extension or a similar flavor of problem. And this is becoming very important as we launch more and more vehicles where we get these embedded solutions in these vehicles. And we think there are a lot of technical challenges that we have to overcome in these to actually provide very good solutions in this space. And finally, when we talk about learning and predictions, what do we mean, right? So basically, these systems inherently are uncertain because of the state of the network, like I said, and of course the user itself. The user asks for a service from this system. We don't know what's the context of the user, right? User is in a hurry, catching a flight, so there's a low variance route might be more important there. The user is a local, so familiar route is more important there. Or the user is a traveler. Yeah, thank you. And so on. So how do we deal with these different user preferences, right? So we found that there is a class of online learning models that can be very nicely adapted here, both in bandit settings and expert settings, where we have explored different probing models using auxiliary information to actually improve the performance of these learning systems. And we got some very good results there. And hopefully this will translate to some very interesting implementations and applications in the space. And the last big area here is not last, but one of the other big areas is understanding the network itself, right? So like I said, we have all this information. Now, how do we succinctly deal with this information? That's representing it is one. And of course, getting this information itself is the other. So can we basically understand this network better in terms of how we get the information, what we call the quality of our lens, right? The quality of lens that you focus on a particular part of the network to get information about the state of the network, right? And that itself is a non-trivial problem. And there are a lot of problems that come up in this space. And of course, learning representations is the classical embeddings and all the related work that is there in the space that could be used to basically represent these networks at the right granularity so that the model change, the model dependencies and correlations in the network. And of course, they're useful to answer the queries you want to answer with very low distortion. So, so here again, we are looking at different deep learning architectures here to see how we can answer these questions. And like I said, one of the important things is this capturing this information in multiple scales and across time. So there's spatial and temporal changes. And also you would like these embeddings to make sense. So if they are, they should have some nice properties that if they are close together or they're representing the same space that is close together, then they should be similar. Or if there's some kind of Lipschitzness, if you will, of change in time and space. So we should be able to satisfy these properties as well, right? And then finally, unlike say the distance oracle kind of settings, here the other key requirement is that they generalize to multiple tasks, right? So you would like to be able to answer shortest path queries. You should be able to answer, use it for predictions, ML models for predictions in speed predictions, for example, event predictions, traffic jams and such. But it should be exactly the same, representation that could be used for all these applications. So that's another important criteria here for problems in the space. So yeah, so I think this is basically to just give you a flavor of all the things that we do. And it covers a lot of areas that could be of potential interest to many of you in this room. And we welcome you to talk to the folks here and learn more about what we do and encourage internship and student researcher applications. And yeah, any other questions? Happy to answer. Thanks.
We have time for a question. Guy, do you want to start setting up, Paul? Is there someone have a question?
Hey, thank you for the great talk. My name is Vinod. I'm a data scientist. So coming from that perspective, I have a question about, so it's not an understatement to say like, at least half the world uses Google Maps for directions, like finding directions. So there's also with large number of users using that, right? That in turn affects the traffic and the flow network. So other models or algorithms or approaches that take into account that feedback of like users using and thereby changing the network properties and thereby changing and like adapting to that. And how does that work?
Absolutely. So we do use that, right? So that's the quality of the lens I'm talking about. You do get information from the network feedback that gives you an update of what the condition there is and so on. But how accurate is that? How believable is that? How real time is that? So these are all questions that come up as we. But yes, absolutely, we do use it.
Right, and next speaker is Guy Rufflet from Apple. He's going to tell us about verifiable data science.
Great. So I wanted to tell you about